So good morning, everybody, or good afternoon, depending on the geographical location that you're in. I am happy to start as a moderator the new web seminar. My name is Andrea D'Aquino. I'm the chair of the working group number 4 in 5G-ACIA. And today I'm happy to present you two of our members, which will be also the speakers of the two different sessions. But first, I would like to go through some housekeeping information with you. So that's me. By the way, I have some troubles in turning on my webcam today, so apologies for that. And okay, so these are the housekeeping information I was talking about. There will be a dedicated question and answer session right at the end of this web seminar, not at the end of each sessions. If the time should not be enough to answer all this question, of course, you have some contacts there to become a member of 5G-ACIA. You can contact the organization also at an email address that you see in this slide. This webinar will be recorded and will be made available on the web on the 5G-ACIA website approximately a week from now, I would say. And should you have any technical question or any issues, please use the chat or write an email to the email address that you see. Everybody is muted, of course, and will be unmuted by default at the end when there is a question and answer session. But let's start with the first session. I'm happy to present you Johan Bergman, who is a master researcher at Ericsson. So the first topic of Johan, if you could go to the next slide, please. It's about RedCap, and I'll leave the spotlight to Johan.
Great. Let's see if I can share here as well. So you should be able to see my screen now, I think.
We can see your screen, but not in the presentation mode.
Oh.
Okay.
Like this.
Yeah, perfect.
So yes, my name is Johan Bergman, and I'm with Ericsson. I work with standardization in 3GPP in working group round 1, and I've been the rapporteur for the work in release 17 and 18 that we will be discussing next year. And so the topic for this webinar is reduced capability, or RedCap, 5G for industrial IoT. And we have written a white paper which should be available very soon at the 5G-ACIA webpage. And today we will, after an introduction, have a look at these new 5G device types with a lower complexity compared to normal 5G devices that we have been specifying support for. And then we'll have a look at some techniques for reduced power consumption for devices, and briefly discuss the applicability and usefulness of these new techniques for industrial IoT use cases before we conclude. And so to start, we can have a look at the traditional 5G usage scenarios. ITU, quite a while back, defined 3 usage scenarios for 5G as part of the IMC 2020 requirements. And they are known as enhanced mobile broadband, EMBB. That's what you have at the top in the triangle to the right. And enhanced mobile broadband is a typical example. There will be smartphones where you want to have high peak rates and good latency. But on a best effort level. Then the second usage scenario was ultra reliable and low latency communications, URLLC, which you find in the lower right corner of the triangle. Maybe industrial robots and self-driving cars could be good examples there, where you have little to no tolerance for errors and unpredictable latency. And then third usage scenario is massive machine type communications, MMTC, or massive IoT. That's the lower left corner in the triangle. And typical examples there would be utility metering devices, like gas and water and electricity metering devices, but also many other IoT devices. And for massive IoT or massive MTC devices, the peak rate and latency is not so important as the device cost and the power consumption, and maybe also the coverage, since some of these devices are in basements and metal enclosures and such things. So it's quite different requirements on these three usage scenarios. But 3GPP is release 50 and supports these three usage scenarios. The first two, EMBB and URLLC, are supported by the 5G radio interface, known as NR or New Radio. And the massive MTC usage scenario is primarily supported by the LTM and NB-IoT technologies. And LTM and NB-IoT were actually specified as part of 4G, but they also fulfill the 5G massive MTC requirements. So both 5G NR and LTM and NB-IoT are considered part of the 5G technologies. And this is all good, but it was realized a few years later, after the first 5G release in release 15, that there are some use cases that fall in between these three usage scenarios. And you can find them in the middle of this triangle here. Representative use cases that were identified were wearables, industrial sensors, and video surveillance. And they all need decent peak rate, latency, and device cost, but not as extreme as any of the corners in the triangle. So then 3GPP set out to address those use cases in releases 17 and 18 by introducing new device types. And these new device types are known as reduced capability or RedCap devices. And these RedCap devices are less complex and can therefore be cheaper and smaller. So next we will then look at the use case requirements, and here I'm focusing on data rate and latency without really mentioning the numbers. You can find them in the white paper. But it should be noted that many of those use cases in the middle of the triangle, they can already be served adequately in many cases by 4G devices, more specifically the 4G LTE user equipment, UE categories 1 to 4, the lowest categories that were defined back in release 8. And you can see the peak rates in the table. We have downlink and uplink peak rates for device categories 1 through 5 in LTE. So you can see that in downlink it ranges from 10 megabit per second to a few hundred megabit, and for wearables and many of the other typical RedCap use cases, you could actually use 4G LTE UV categories 1, 2, 3, or 4. So then we went ahead in release 17 and specified a number of simplifications for the devices to reach similar performance and complexity as those low-end 4G device types. So that included primarily these 5 techniques here. And the first one is reduced maximum bandwidth, and that's actually, as you can see in the illustration, the only mandatory feature for a RedCap UE. All RedCap UEs need to support they have the bandwidth restriction. All the other simplifications are optional, so it's up to the device vendor to decide which ones to implement. So the first one is the reduced maximum bandwidth for transmission and reception. And we will come to the details a little bit on the next slide. And when the bandwidth is reduced, the peak rate is also reduced proportionally. Reduced number of antennas, and somewhat related, reduced number of MIMO layers. MIMO is multiple input, multiple output, and layers means essentially number of parallel streams in the air. Using antennas in a clever way, you can transmit more than one stream if you have more than one antenna. And then also some reduction to the maximum modulation order. The modulation order determines the number of bits you can transmit in a modulation symbol in a time period in the radio wave. And the fifth one is half duplex operation. UE device, or UE, as we say, that supports half duplex only cannot transmit and receive at the same time. So a typical device nowadays would be full duplex, meaning that it can transmit and receive at the same time. But if you implement all these things, then you have a potential complexity reduction of 50 to 70% of the UE modem radio and digital parts. The actual complexity reduction depends on what frequency bands the UE supports and on other implementation choices. So I will not go into detail here, but I just want to show the tables that we have in the white paper. Here you can see a comparison between ordinary 5G UEs and release 17 RedCap UEs. And it's a bit different for different frequency band. We have low, mid, and high frequency bands here. And the ones that are about to reach the market are for low and mid frequency bands, I would say. And I guess we'll see if we also see some RedCap products for high frequency bands. So if we look, for example, at low frequency bands, you see that an ordinary 5G UE needs to support at least 100 megahertz bandwidth, at least in bands that are that wide. Whereas the RedCap UE only needs to support 20 megahertz. It's actually not allowed to support more than 20 megahertz. So that's one of the biggest complexity reductions. Then when it comes to the number of antennas, an ordinary UE 5G UE needs to support at least 2 antennas in low bands, whereas RedCap UE can support maximum 2 antennas. So it can support as few as 1 antenna. And similarly, it doesn't need to support this MIMO parallel stream transmission. And it can support a bit lower modulation, and it can support half duplex. But as I mentioned, most of these things are optional, so it's up to the device how low complexity to target, and that has some implications on the peak rates or data rates in general. So we have another table here then with some example peak rates for release 17 RedCap UIs, and it's also different for different frequency bands, as you can see. So if we look at low bands for you have downlink and uplink peak rates here, and first row here is a bit of a special case, so maybe we focus on the next two. Single layer 64 QAM, that's if you have the lowest number of antennas and MIMO layers and modulation order, you get this kind of peak rates of 85 and 90 megabit per second in downlink and uplink respectively. And if you want to support 2 antennas and 2 MIMO layers and a little bit higher modulation order, then you get about 200 megabit downlink peak rate. The uplink peak rate is not affected. Most of the complexity reductions are related to downlink, since the receiver is the more complex part in the device. So, and these peak rates are then somewhat similar to what we have for the 4G LTE UE categories 2, 3, and 4, both when it comes to complexity and peak rates, which means they're a little bit higher than what you have for the very simplest 4G UE category, which is known as category 1. There's also a category 1 BIS, which is the single antenna version of category 1. So, and since there are use cases that might benefit from, but they don't need the higher peak rate, so they why not let them benefit from a little bit lower complexity. So in release 18, we introduced enhanced RedCap, eRedCap. I'm not sure enhanced is the best word, but that's what it's called. So we introduced in release 18 eRedCap UIs with a peak rate capped to 10 megabit per second. So it's a bit lower than the numbers I just described on the previous page for release 17 RedCap. And with that, we have peak rates and estimated complexity on par with 4G UE category 1 or 1Bs. So therefore, I think we can say that RedCap and eRedCap UIs provide a migration path to 5G for use cases that are currently served by low-end 4G UIs, and hopefully we can also serve some new use cases. So that was about the new RedCap and eRedCap UI types. Then we also specified support for some reduced power consumption techniques. And as you can see, quite a few power consumption reduction techniques have been introduced in 5G releases 15, 16, 17, 18, 19. And most of them can be supported by RedCap and eRedCap UIs as well. It may even be so that the first UIs we see supporting some of these techniques are actually RedCap UIs. And the techniques specified in 5G release 17 and 18, so at the same time as the RedCap and eRedCap UI types, they have the potential to extend battery life to several years under certain assumptions. And this is mainly achieved by increasing the sleep opportunities for the UI's receiver circuitry. And it should then be noted that if you use or configure and use or assume very long sleep cycles, there will be an impact on downlink latency, because now we have a specified support for up to almost 3 hours sleep cycles, which means that the network cannot reach the UI until it wakes up after 3 hours. So that might not be a suitable configuration for most use cases. There is no impact, not really any impact on the uplink latency, since the UI is always allowed to access the network at any time, more or less. But it should then be noted that if you have use cases that require low latency in downlink or frequent data transmission in uplink or downlink, then you may not benefit as much from these techniques, since the UI will in practice not be able to sleep as much. So that needs to be considered from case to case. When it comes to the industrial IoT use cases, many industrial IoT use cases should be able to benefit from these new 5G features for lower device complexity and power consumption. And in the white paper, we have chapter 6, which discusses different use cases, different types of wearables, wireless sensors, video surveillance, handheld radio devices, 5G mobile trackers. And so that should be interesting reading, hopefully. And some network aspects to highlight is maybe that to support these RedCap or eRedCap UEs, the network must support 5G standalone operation, which is the case in quite many networks now, but there are also still many networks that have not yet introduced support for that. So they support 5G non-standalone operation, which means that you rely on 4G to some extent. So the networks need to be and will hopefully be upgraded to 5G standalone operation swiftly. There is one other aspect to keep in mind. If RedCap use with reduced number of antennas are used for traffic-intensive high-throughput use cases that they are not intended for, there may be an impact on the overall capacity of the network. So care should be taken to use RedCap devices for cases they are intended for, if you want to avoid any drawbacks. So to conclude, 5G releases 17 and 18 introduce new, less complex device types. The network must support 5G standalone operation to support these new device types. And then 5G releases 17, 18, and 19 enable lower device power consumption under the right circumstances. And hopefully many industrial IoT use cases may benefit from these new features. And you can read all about it in the new white paper. Thank you.
Okay, so many thanks for this wonderful presentation about RedCap. And I have the pleasure of introducing you to the next presentation from João. And this will be about machine vision. João?
I'm here. just give me a second.
Sure. So João Lopes is Technical Project Manager at NXP. So João, the stage is yours.
Okay. So thank you, Andrea. So as you said, I'm João Lopes, Technical Project Manager at NXP Semiconductors, and I'm here to present you a white paper that we did at 5G-ACIA, which is the architecting technology of machine vision industrial applications with 5G. So this white paper has this structure, as you see, the introduction, use case and requirements, architecture technology options, and then how to map these to machine vision systems with 5G, and then we come to a conclusion. You can find this white paper, it's already available at 5G-ACIA website. So, to introduction. We started this white paper because there is a belief that machine vision will play an increasing role in industrial automation. And why? Because for one, there is a big trend to do as much as possible standardizations that are OSI layered. And this allows you to have different use cases shared by the same technology, and by that you reduce the development costs. What you do can be applicable in different market verticals, and you can only focus on the part that you are good at, that your company is good at, because it is OSI layered. And this is one topic or one perspective. The other perspective is that with the usage of artificial intelligence, the potential applications increase dramatically. So I give you an example, and this is happening today already, that in the past you were using vision just as a sensor, but now you already have vision-guided automation. So you already have been picking applications using artificial intelligence guided by vision. So, and we had a methodology to make this white paper and to classify the different use cases and derive the requirements. So first of all, we collected what we consider as the relevant machine vision use cases, and considering use cases in factory automation, process automation. So we come up after clustering the different use cases to 7 stationary use cases for mobile use cases. I'll go through them in the next slide. But then what we did was also to have a systematic description of the different use cases. So first, the description, and then what were the preconditions before any event was supposed to take place. Then the service flow to serve this concrete, let's call it automation event. And then what are the post conditions after this happened, and what are the requirements to fulfill this flow. So you can see here what the use case that we defined for stationary use cases: process automation for plant asset monitoring, then augmented reality-based product quality and augmented field procedure using digital twin, then augmented reality for remote operation, then inline multi-camera manufacturing, inline multi-camera quality inspection, bin picking that I mentioned already before, and collision warning system. This is just a list. The description, as I told you in the slide before, it's on the white paper. And then to the mobile use cases, we defined 4: mobile robots and autonomous guided vehicles, autonomous navigation, obstacle detection and code reading, and finally, autonomous mobile robots remote operation. So, and then to have a short introduction on the architecture and technology options, we defined that there is a machine vision system is a system that comprehends at the end 3 different parts. So you have the optical setup, including the lights and the lenses, and have the interfaces. And then you also need to define what are the process requirements so that you can integrate this machine vision system in what is here so-called automation pyramid, and at the end be part of the automation process. So to the optical setup, machine vision camera as an image sensor, the lenses, and it has an image data process, which may be inside or outside. And for that, there are 3 main system approaches. So you can have, and you can see that on the left-hand side in this picture, you have a machine vision camera system, and then you have the smart camera and vision sensor integrated, and then embedded vision system. So from the left to the right, it's in terms of size. Okay. So regarding the vision sensor interface, nowadays there is mainly low voltage digital signaling and MIPI. MIPI is what you can find easily on your mobile phones in the cameras. There is also a specification on how to map this MIPI standard or interface over IEEE 1722. Then on the transport layer, options that you have to convey this vision data. Nowadays, in industrial scenario, it's mainly GigaVision, the technology that is predominant today. But as I mentioned before, there is already a specification to map MIPI over IEEE 1722. And this will enable TSN usage for machine vision. And how, as I was saying in the previous slides, because it's layered and because you can focus on what your technology that you are developing, it also enables you this layered architecture that you can use, for instance, this machine vision for automotive as well, not necessarily only for automation. And that's why it is very interesting, this mapping over IEEE 1722. At the end, then, for the configuration, you have the application layer interface, and this is nowadays the most commonly used is GenICam. And now to the process requirements. So why do we believe that 5G has a very high potential to serve machine vision in factory and process automation? So I think I can divide this in two main topics, the 5G key features. So you have the three first ones, which goes around the integration of machine vision and 5G. So it is because 5G is IT native, it is easy to integrate 5G in the existing enterprise resource planning systems. And it's also easy, the integration with existing industrial communication system, because it's layered and standardized. And then this also allows for a easy deployment at edge computing. Then you have the features that 5G additionally also has. So you can have multi-parallel flows in one device with different requirements. Because it's wireless, you have a flexible coverage. It has the network slicing. For instance, if you have something that is safety critical, then might be that you want to have a slice that is dedicated for that, so that you are sure that safety critical communication is ensured. And then last but not the least, you also have positioning services. And that is why 5G can be so interesting for machine vision in industrial automation. So with that in mind, as you can see on your left-hand side, we come up with different vision system scenarios considering 5G. So the first one, you see there is a backbone wireless. So there is a camera, which then connects to a vision industrial PC. So it's where the compute of the vision takes place, and this is wired. And then over 5G, you send information over to the controller industrial PC. So the industrial automation application controller. The second scenario is when you have the integration between the embedded vision compute and the camera. So you have a smart camera, and then goes directly from this smart camera to the apps processor for the automation application, the control industrial PC. Then the third one, there are two subclasses. So the first one, you have cameras that already have a 5G interface, but they have the capability of pre-process the image data. This information is transferred over 5G for the embedded vision compute, which then transmits information again to the automation controller. Then the second variant is that you don't have pre-processed image data, so you have raw data from 5G to the embedded vision compute. And here you can expect that data throughput must be much higher. So, and to understand how can this map in concrete with 5G, just a small introduction. In 5G, some dedicated information. So 5G consists of two major building blocks: 5G network, where you have the core network and the radio access network, and then the 5G user equipment. And here you have two possibilities of integrating 5G with the different devices. So either you have, as you can see on the left-hand side, integrated device, so the sensor, for instance, the vision sensor as a 5G modem and then can communicate directly, or you have IO gateway, 5G gateway, that then it may be converging information for more devices or just be dedicated to one device. And it has also some processing capabilities. And afterwards, then it will transmit information to the 5G network. So having that in mind, plus the use cases, we come up with three different use cases or possible integrations of machine vision systems with 5G. This first one, at the end, if you remember the previous picture when there was these different use case scenarios, you see that the the camera here is not integrated with the vision embedded compute, but can also be. So here, from the 5G perspective, if the vision embedded compute is integrated in the camera or not is of second order. Important is what is the communication requirements between the compute and 5G. Therefore, this first case, number one, integrates the previous two cases. So either smart camera with integrated embedded compute or separated. And here, what happens is that you have an automation controller that controls the automation process, which then triggers the vision compute. This vision application that is running on the vision embedded compute then steers the industrial manufacturing process. And therefore, what happens at the end of the day is that you have a modest bandwidth requirements. So you have a few kilobytes from 10 to 100 kilobytes just for the control. And then you might need for monitoring some video transfer from the vision embedded compute to the vision control compute, so the automation controller, to make sure that you are monitoring the process and the process is running as expected. I'm not going to go into the details, but below in this picture, you can see how the protocol stack view looks like. This is, of course, on the white paper document. I'll be glad if you have a look into it. But here exemplifies how this can look like in real world. Then the second case refers to the case 3.1 on the picture where everything was resumed. And here, what you see is that the camera is separated from the vision compute and is only, therefore, pre-processing of the vision data on the camera. And with that, you can expect a considerably higher throughput requirement. And it has, therefore, some implications. Depends on the number of cameras you have. This might become a bottleneck. Here, it can make sense to have IoT gateway, so a 5G gateway, so that you can use some of the potential available processing on the gateway to do some of this pre-processing. This is up for consideration, but you can also, it is feasible that you have embedded UE here. And again, the protocol stack overview, you can see it here. It's also on the white paper. Then the last use case here, it's what was on the overall usage scenarios, the 3.1. Here, the cameras do not do any pre-processing at all. It's just sending raw data. And these can be a very big amount of data depending on the resolution of the cameras, depending on the number of frames per second that you have to send. But either way, it will be by far the one that will require higher bandwidth. It has the advantage of being much simpler as well. But it has the 5G can become, not just 5G, but the 5G also can become a bottleneck here. So I said there is no pre-processing. And one important piece of information as well is that because these systems or this solution is seen as to be a very small device, it's not likely to have some embedded UE on these cameras. So it's very likely you will need a gateway, which could maybe be considered, if you have the available performance or processing performance, to do some processing, and with that you could have some gains. But as said, the data throughput requirements are here extremely high. And again, the protocol stack, how this could be made, is here and is also defined in the white paper. So concluding, 5G is a flexible technology that at the end it can be very helpful in factories that tend to be, I wouldn't call it moving or changing the layout every day, but this happens, but every month is something that is pretty much normal. So avoiding cables and using a wireless technology like 5G can be very beneficial. And because you may have some different quality of services, some KPIs, 5G can be very handy here because you can locate those just by configuration. And it was also as outcome from this white paper that 5G can support a very relevant number of machine vision use cases today. And there is, we can be confident in the future that by having this standardization efforts, not just on 3GPP side, but every side. So you have the camera interfaces, you have also the automation interfaces, because everything is using a layered architecture. I think that it is, one can say that this is a trend that is going to increase. So the usage of 5G, making usage of this layered architecture is going to increase in the future. And thank you.
Thanks, Joao. With that, we come to the question and answer session. So I see, I'm looking right now at the Q&A tab and the chat, and it appears that there are no questions. So I would just to make sure ask support of the office, if you could tell me if I'm correct, there is nothing. And in that case, I have actually a couple of questions. But let's maybe give 30 seconds more to people if they would like to type some questions for our speakers. In the meantime, maybe I can ask already my first question. So I have two, actually, one for Johan and one for Joao. The first one is for Johan, actually. And so you talked a little bit about several configuration of RedCap. And just as a hint for our audience, I would like to ask you about your judgment for what you consider to be the largest use case for RedCap devices with 5G.
Well, it remains to be seen, I guess, but I think we expect the wearables to become a big thing eventually, but maybe not in the first wave. I think in the first wave we see more router-like things.
Mm-hmm. Okay. And then there's a question in the chat. I guess that's still for you, Johan. Are there any plans for a true 5G alternative to NB IoT? I'm not sure what true alternative stands for. Is this about I don't know. Is there any aspect that you would like to specify, or
so these massive MTC technologies, or LPWA technologies, as they are also called, there is no dedicated 5G technology unless we, for massive MTC or LPWA, unless we count NB-IoT and LTM, which are considered to be 5G massive MTC technology since they fulfill the 5G MMTC requirements. But there may be cases where RedCap or eRedCap can serve as a substitute for NB-IoT or LTM, for example, if you want to support this type of use cases in mid-band TDD bands where NB-IoT and LTM don't really have an ecosystem. So in some cases, RedCap or RedCap can serve as a substitute, even though it doesn't have the same extreme low complexity as LTM and NB-IoT. So I think we expect the replacement, the sort of true replacement of LTM and NB-IoT to happen in 6G timeframe instead.
Okay, thank you very much. And so I hope the question was answered. If not, then please specify if there is a point that wasn't covered by the answer. Otherwise, I have a question for João. So about one of your last slides, you mentioned there is a use case for cameras which do not do any pre-processing of data and might transfer the raw data, and of course for that is a lot of bandwidth is to be used. And again, my question is on the use case. Where would you envision such a use case to be present? Is this a very niche thing, or is there? Can you make an example of it?
Yes, I think that if you don't have limitations on the bandwidth, for instance, if you have just 2 cameras, but you have very high requirements in what regards to latency and also the image data that you want to process. Imagine that you want to avoid collisions and in something that is moving, and if it is high latency, then probably this functionality would not be possible. Or the processing of data, the algorithm that will evaluate if there is something blocking your path or not. If you have already some pre-processing of data, maybe this is not possible. And therefore, there might be a case where you think, okay, I still need to live with a huge bandwidth because at the end of the day, I need that to have the full information and I have the required low latency. But this, as you said, I think this more like as a corner cases.
Mm-hmm. Yeah, I think if I am allowed a further comment, I think it's a little bit the beauty of 5G, right? You have very different very different scenarios that you can cover with the technology. Yes. Do we have any other question on? Again, I'm switching through Q&A and chat. So if you can see anything, just say the word. Otherwise, I don't see anything else. And if this is not the case, then if I can ask Office to show the last slide with our contacts. Of course, you can follow us on LinkedIn to stay in touch. And of course, if you would like to ask more questions that we didn't see here today, you're welcome to do so. You're welcome to contact us. And by the way, we do have a web seminar series coming up, and this was the first of that series. So stay tuned, and we'll let everybody who is following us on LinkedIn know when these webinars are coming up. Thanks, everybody, for the attendance and for your attention, of course. And I hope to be able to see you during next webinar. Bye-bye.